Yes, you can start.
A very good evening to all respective dignitaries, faculty members, and participants. It gives me a immense pleasure to welcome you all to the 8th session of ATAL Faculty Development Program. We are delighted to have an enthusiastic gathering of faculty members who are keen to enhance their knowledge and engage with emerging technology. We now move on to the next technical session titled Powering the Future. Exploring the neural network architectures with renewable energy data. The session focuses on growing role of neural network in transforming renewable energy system with the increasing availability of large scale energy data. Advanced neural network architectures are becoming enhanced tool for accurate prediction, optimization, and intelligent decision making. The session will explore how renewable energy data can be effectively modeled using a neural network to address key challenges such as intermittency, demand forecasting, and system efficiency. It will also provide insight into current trends and future possibilities at the intersection of artificial intelligence and sustainable energy. We hope this session offers a valuable learning and inspires involved thinking among all participants. Let us now begin the session. Now I call upon Dr. R. Saranan to introduce our guest lecturer.
Thank you. It's a moment of great privilege and honor to introduce our distinguished research person for today's session. We are delighted to have you with us, Mr. Ganesh Suresh, a highly accomplished artificial intelligence professional with over 12 years of rich experience spanning industry, research, advanced technology development, and high impact training. He is currently serving as a senior AI architect at Ericsson Chennai, where he has played a pivotal role in designing, architecting, and deploying scalable real-world AI-driven solutions. His area of expertise include artificial intelligence, machine learning, deep learning, neural network architectures, data-driven system design, and intelligent automation. Over the past decade, he has been actively involved in delivering more than 800 technical workshops, faculty development programs, guest lectures, and international expert sessions, reaching a wide audience across premier institutions in India and abroad countries such as Singapore, Moscow, Germany, and Prague, etc. His sessions are widely appreciated for his clarity, strong conceptual foundation, and excellent industrial relevance. He holds the distinguished recognition of being a speaker of India Book of Records, honoring for conducting one of the largest artificial intelligence workshops involving over 1,000 participants. He also served as a youngest judge in the year of 2019 in Smart India Hackathon and even addressed by the Honorable Prime Minister Sri Narendra Modi sir. His contribution to technology and innovation have been appreciated by the Dr. APJ Abdul Kalam sir, former President of India, particularly for his work on humanoid robot development. He has delivered expert lectures and workshops at prestigious institutions such as IIT Madras, IIT Hyderabad, IISc Bangalore, NITs, VIIT, Anna University, SRM University, as well as PSNI College of Engineering Technology, and many others. In addition to training and mentoring, he has published research papers in international conferences and worked on several impactful projects, including humanoid robots, AI voice assistants, medical AI systems, computer vision application, GAN architecture, and traffic sign classification systems. What truly sets him apart in his ability to bridge the gap between theoretical AI concepts and their real time implementation in emerging domains such as renewable energy, sustainability, intelligent systems, and future ready neural network solution. With this vast industrial exposure and passion for knowledge sharing, today's session on powering the futures, exploring neural network architecture with renewable energy data promises to be a highly insightful and engaging and inspiring for all the participants. On behalf of the organizing committee, I extend a warm and heartfelt welcome to our esteemed speaker, Mr. Jay Ganesh Suresh, and invite him to take over the session. We welcome you, sir.
Yeah, thank you, sir. Thank you so much for the brief introduction. Thank you so much once again. So, just a minute. I take a minute to share the screen for here.
Okay, sir.
Yes. All right. So, very good evening to all. Very good evening to one and all present here, to all the esteemed professors and all the esteemed doctorates and also scholars. I'm very happy to be here, first of all, to give the lecture on neural network architecture. And the agenda of this event is all about a generic neural network architecture. So how neural network architecture is works and how neural network architecture really helps and how neural network architecture, some of the components we will be having, right? We will be having like loss function, cost function, the weight visualization, and gradient descendant methodologies and error stoppings or early stoppings. And alongside, we'll also discuss about some of the strategies of overweighting and underweighting. So these are the parts we'll discuss over now. And on top of it, we'll go for the hands-on. So I have a hands-on code where we have a deep learning architecture. So deep learning architectures of neural networks. Plus, I have used a data set of power energy saving data set. It's not exactly like an EV one, but it is like a solar panel data. So you can give the some got attributes of, for example, temperature and the relevancies, and as well as you can give these components. And based on these components, your model will say what kind of power you can derive from the solar panels. So based on the temperature, based on the wind speed, it will be telling you like, oh, what is the derivable energy from the solar panel. So this is a data set I have. So through this, we're going to have a predictive analysis thing. And in that predictive analysis, we have a train model and testing model. That testing model takes your data and predicts. And in train model, we're going to compute train set error and testing set error. Okay, so this is a short agenda of what we're gonna see in the upcoming session. So the for the next 1.5 hours, we're gonna wrap it around with this topic. Let me get begin with artificial neural networks. Since I hope though, like most of you been walking through some neural network architectures and the convolution neural network architecture. So here I'm not going the base concepts in a very deeper way. So I'll go to the technical concepts in a very deeper. So that would be much more helpful for all of you. I hope so. So artificial neural networks, like artificial neural networks is a system, it's an architecture, how the human brain thinks and how the human brain function, the same way neural network architecture has been touched from. So it takes the user input, process them, and connecting to the next set of neurons. The similar way takes the input layer, you're taking your inputs and processing them here and delivering in the output layer. This is what artificial neural network generally reacts and works for the data. Now, how single neuron generally works that you may aware of it, like it takes various inputs from the previous layers and takes the value and decides whether the value is a valid value or not. If it is valid, then it will be connecting to the next layer. And you could have asked me, okay, is it the same for all the neurons within an architecture? Of course, true. Each architecture, each neurons of your neural networks deals the same and functioning the same. It takes the previous data, functioning them, and activate if it is a valid information. It will not get activated. So this is the same functionality which happens across all the neurons of the neural network architecture. And how it actually works. So here I'll take a moment to explain. So here I can take a moment to explain. Just a minute. So just a minute. I'm getting some call. Just a minute, please. Excuse me for a moment.
Okay, sir. Participant, kindly wait.
Sorry, I'm back.
Sir,
Yeah, sir,
your
I'm back.
voice is very low, sir.
I'm audible now, sir. I'm better.
Audible, sir, but very low, sir.
Is it better now, sir?
No,
While
sir.
better?
Are you using headphone or
No,
just
I'm using no professional headphone only, sir. Am I
okay,
audible
sir?
now?
Audible, sir, but low, little bit low, sir.
Okay, students first. Am I audible, sir, now?
Yes,
Better?
sir.
At least now, no better,
Audible.
sir?
Yes, sir. Yes, sir.
Okay, okay. I'm changing the input actually. That's why I'm just checking it. So we
Okay,
can
sir.
ensure now, sir. I hope it is better now.
Okay, sir.
Oh, fine, sir. Um, yeah. So again, I'm continuing with the part. It's still visible. So yes, how it actually works, it is considered you are having an images. Okay, so of course we want to see the data in respect to like the CSV formats, and I'll tell you like how to calculate that. But here we're gonna have the input is like an image. So image is all about like a height and the width. Consider each pixel. So 28 cross 28. So 28 cross 28 in the sense is close to like a 784 pixels. 784 pixels in the sense each neuron will take each pixel. So that means we'll have a 1, 2, 3, until we have a 784 neurons we will be having here. And each what is that pixels will assigned by each neurons and it will be processing it. This is how your neural network architecture takes the input. So it's the first process. And the next one is when it is processing from here to there. That means this is your input layer and this is your hidden layer 1 and this is your hidden layer 2. Okay, so when it is processing to here and it takes the value, consider like a 0.27, okay, and 0.1. So each value is 0.37. So what we'll do is we are not just passing this 0.27 just like that to this neuron. Okay, now we are not directly passing the 0.27 to here. We are not just directly passing the 0.37. Instead, we are adding some knowledge on top of it before we are transferring that to the next layer. So what is the knowledge? Well, knowledge in the sense it is like a weight. We can call it as a weight. So we'll add a 0.27. Alongside, we'll add a weight. So weight in the sense some value like a zero point 0.1 or something else. Well, and we'll be adding some bias. I'll talk about what is the bias. For now, you can consider zero point 0.1. So we will be doing this process, and after this computation, this value will be added. So you could have asked me, why Jay, why this is so happening? So we can directly pass this value to the next layer instead of doing so and so. Think about it. If I give this value directly to the next layer, there is no use of course. Reason is because we are not going to memorize our data. We are not just going to learn the data. We are not making just a learn. We wanted to make our architecture to learn it to the next level so that we need to add some additional weight on top of it. That weight will help to will help to make your architecture to understand the data next level. Consider a simple example. I studied the neural network from books. Okay, I have studied from various books. So now Jay knows. So now if I communicate the same with my audience, okay, if I study what I studied in the books, same if I cover the same, that's of course the same. Of course, there is no use because I studied with respect to the equation, I studied with respect to the calculation, I studied with respect to with very wage and weight concepts. So I cannot deliver the same. So in order to that, I will be taking this data and I will be adding my knowledge on top of it. So I'll be adding my experience, I'll be adding my knowledge. On top of that, I will be delivering that content to all the audience whoever is looking for. So that means I'm adding the weight on top of it. That is a call here. So instead of just getting and transferring, I'm adding some weight. That weight will create a non-linear relationship between an input and output. So if you're not adding the weight, your entire neural network architecture will behave as a what is that linear layer. Okay, it looks like a linear regression. So linear regression. For that, you can go for a linear regression itself to do this process. Okay, so that is how this process will happen. And once this is process happen, you can able to see there is other function. Okay, so now all the process is done. We are having some value 0.1, minus 0.2, minus 0.3 and minus 1.2 or something so and so. Okay, now we are having an activation function. So I'll come to that point. So this is a weight initialization. This weight can be like a normal distribution or else it's like a randomized distribution. Okay, so normal distribution since is generally zero point 0.1 or something else, and randomized in the sense each and every layer or for not each and every layer. So each and every back propagation, this weight will be 0.2. Okay, so this is how actually this weight calculations will happen during the initialization. And here we go for the neural network activation function. What is an activation function? Activation function ensures whether the neuron is having the valid information or not. If it doesn't have the valid information, it will not get activated. Then it will not be passing that information to the next layer or the next neuron. So unless it has the valid information, it will not get activated. That means you can understand the same. Okay, Jay. So now you are saying that like a 0.1, 0.2, 0.3, and 0.4. So if your neuron is considered this is a valid value, if your neuron considers this is a valid value, then it will be communicating to this layer. If this is not been considered, it will not be connecting to other neurons. It will be dumping the values. We are dumping that neurons, so this value will not be communicated. So it will be converting into zero. Okay, this neuron will not communicate any value to the next layer at all. Okay, this is a kind of a dropout we can say. Okay, this is how your activation function is written helps. Maybe we can go much technical. And in simple short and technical, if you ask me, this will help you to create a non-linear relationship between the input and the output. Non-linear relationship in the sense I don't want to study the book and I don't want to vomit to everywhere. So instead, I need to add my an ideology and I will have to deliver the content to the next level. So this is the same. I want to create a non-linear relationship between an input and output. Okay, so again, if you see like a activation function. So we have a various activation function. So one is threshold, ReLU, and sigmoid and hyperbolic tangent function. These are the four popular activation function. And apart from we have what is that some softmax functions we are having, and apart from we have a linear and everything. But this four of them mostly fill under most of the cases. Let's go through one by one. Most famous is like a ReLU. Most famous is ReLU, and most of the neural network architecture, apart from RNN architecture, we are using ReLU as an activation function, even in the RCNN, even in mask RCNN, even in YOLO, everywhere we are using like a ReLU activation function. And wherever you have an output layer, during output layer, we use threshold and sigma. And I'll give you some stats here. So why we choose ReLU at the hidden layers? What is the use of it? Consider you have this neural network architecture, and here you are having a 0.00012. Okay, here consider like a 0.00013, and here you have like a minus 0.00013, and you can consider like a 0.012 or something else. What your ReLU function will do is since your ReLU function will consider only the positive value. That was it's mentioned like it starts from 0 to 1. It will consider only the positive value. If there is any negative values, that neuron will be dumped right over there. It will not be considered for the computation. So going forward, only these two neurons will be communicating to the all the layers. And you could have asked me the same. Okay, sir. If we are dumping these two values, it may have some valid information of this logo. It may have some valid information of this what is that this tilt line. So is the browser how it could be handled? Of course, you're right, but think about it. Out of 100%, I could have lost like a 20% of information as like this. Maximum 30% of information I could have lost like this by using this negative spectrums. But consider if I include this 20 to 30% also on top of my model becomes so complex. I have to integrate a lot of strategies to handle this negative values to be considered. So that's how we'll not be considering negative values, we'll consider only positive values. So we are having in the thought of if my model understood 70% of the image information, that is fine for my classification, for my prediction. This is how the Lord is all about. Again, not 20 to 30, of course, maximum it will be like a 10 to 15%. That's how it relies on. Okay. And coming to the other part. Okay, sir, what if we use sigmoid? Or what if we use threshold? Consider. So threshold and consider threshold and this and all. If you are having like a consider your set is like 0.00012 and your set is like a 0.123 and this one is like a 0.15 and this one is like a 0.67 or something. Now if I apply threshold, what will happen? So greater than zero point 0.5, greater than 50%, consider that every value is also 1. Less than 0.5, every value considers 0. Now you can see this value will be considered as a 0. This cell will be considered as a 0. This neuron will be considered as a 0, and this neuron will be considered as a 1. Now, if we have this value in each and every neurons, your entire architecture will play with the just zeros and ones. course it's not acceptable. Of course it's not useful, right? Because according to us, we know if your neurons is having like a 0.00001 in the sense that 0.001 is having the valid information of it. So your neural network architecture is handling with the unsigned integer of 8. You could have known about it. So that means 0 point, we'll be having up to 8 digits of informations we are carrying. So just to add, since we are talking about this one, in neural networks, in generative AI architecture, transformer where and all, we'll be using like a floating point. We'll be using like a floating point up to 32. That means after dot, we are having a 32-bit transitions information. So some we'll be doing some predictions by using quantization. That means up to 16, 0 point up to 16-bit transitions. This is how we are dealt with the data. We are processing the data. Okay, so that's why we are not using threshold, why we are not using sigmoid on top of your hidden layers. Then the use of using it in the output layer, reason is nothing but if your problem statement is a classification, your model will decide if the prediction is greater than zero point 0.5, it will decide yes, it's a bird. Less than zero point 0.5, it will decide it is not a bird. So this is how the classification do works on top of this development. Okay. I hope it makes sense to all of you. I hope so.
Yes, sir.
And sir, thank you, sir. So the same thing like we have a psi of x and the max of x of 0. That means your maximum value. So somewhat in the plus integers and your maximum minimum value is supposed to be a 0. And when you come for a threshold, we'll be having if condition greater than or equal to 0, it's 1 and less than 0. Of course, we do consider that as a 0. That's how the psi x is defined. And this still remains same. There is no changes with the weight calculation. The weight calculation, nothing happens. Once the weight calculation has happened, we are doing our what is that? This activation functions on top of it. Okay, still the weight calculation remains. There is no magic on top of it. And the sigmoid also the same. So of x 1 divided by 1, 1 divided by 1 plus or minus. This is how it makes. And when you go for like a hyperbolic tangent function, this is not a for now. This is not a link for now. But this hyperbolic tangent function we are using in the RNN architecture. So in RNN architecture we use this, and we're using in the Gemini architectures too. So that means the transformers, the LLMs, we are using a hyperbolic tangent function because we should consider negative values also for our development. So where you wanted to consider the negative value, when you wanted to predict the next value. So when you wanted to predict a new word, you should have the previous value information into it. Then only you can able to predict the next value. That is why we'll be using a RNN. We'll be using a hyperbolic tangent function on top of. So we're using a hyperbolic tangent function on RNN architecture and generative architectures. We're not going much deep in this, but it's a range of -1 to +1. This how this activation function is realized on top of your development. And this is a simple picture representations I have added here. So you can see that input feature map, you have seen that these are all black regions, some of the prime dark regions, though it's a sharpened one. And when you see after applying the review, we are losing that sharpening and the kind of areas. And of course, you might have think, oh, we are losing some prime information logic here. Yes, as I told before, right? We will be considering only the non-negative values because that's our destiny. We don't want to confuse our architecture. So I wanted to make this value to make a non-linear relationship between an input and output. That's what prime is all about. That's how this is on. And you can also see like that this negative values we are converting directly into zero. This negative values we are directly converting into zero. That means these neurons will be down like this, not be processing forward. That's how it actually tells you the idea. So this is a review equation function. So here I have a simple math which begins of the development. You can see the math we are having a two. Consider this is a one thing. So the same equation what we discussed, right? Summation I equal to 1 to n w into x plus b. I'll talk about b again. So this consider this is your x and star, this is your w, which is equal to 1. So you got a 1. So this is a z equal to 1. So you have a hidden layer value. This hidden layer value should undergo with some activation function. Here we are having a sigmoid. So we are giving this value to the sigmoid. This sigmoid will turn some value as a 8 equal to 0 0.1, 0.7, sorry, 0.7. This is a neuron value of the hidden layer. Okay, and the similar process will happen to the next layer. So x into w, which is equal to zero point 0.5. This zero point 0.5 will be kept into like activation function. That activation function delivers a. This is how your math will happen the behind of your architectures and how the bias really helps here. During the back propagation, two things will update in constantly. One is like a weights and another one is a bias. Because your weights will help you to add a knowledge on top of your bias, ensures your model working on the bias, and it is not and it's not fitting on some issues like overfitting and underfitting. It makes your model to be biased, not to lie over out of scope or something else. Because if your model is learning, your model should learn like this, and suddenly it is shooting. That means your bias is not doing a good job, and your bias is not updated well. So that is what this will happen. So your bias ensures even it's going shooting up, it will bring this bar. This will bring this what is that? This model up. Okay, this is how this bias switch really helps you. And coming to the next point is called like a back propagation. Back propagation and forward propagation. You might have heard about it if you are already into like deep learning. I hope so. And back propagation is a process of updating the weights in order to handle the error interpretation. So in simple concepts like I have X1 neurons, you're processing them. Okay, each and every weight is like a first weight like a point 0.2, 0.8, 1.2, 1.3, blah 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 happening. And consider you are training with the three images. Okay, you're training with the three images. And apple image, this is an apple image. Consider this is an apple result, and this is a banana result, and this is a carrot. And is not a fruit, by the way. So maybe I can add like a kiwi. Okay. So totally we have a three fruit. And this fruit actual image, so you are giving a first image, right? That first image, whether it is predicting properly, actual image value is like a point nine. Actual apple image value is a point nine. Actual banana image like a point zero, and the actual kiwi is like a point zero. So consider this is all for example. I don't like this like what is the 90% also. That means the number of that number represents your image. Okay, so first iteration is done. First iteration, your model predicts this is a one. So we need to calculate the loss calculation. This is called a loss function. So during loss function, we calculate actual minus prediction. Actual original image minus prediction value. So we got a 60% error. So your model still lag with the 60%. So 60% it's not confident to say it's an apple. So that just a 40% confidence to say an apple. Okay, now I have a zero point 0 minus zero point 0.5, so we got like a minus zero point 0.5. That means it's got a negative value again. Like it's 50%, it's unconfident to say it's a banana. And also the same spectrum, you can see it's at 20%. That means 20% your model is less confident to say this is a kiwi. So that means loss function you are computing. So this loss function ensures whether your model is training well or not. By seeing this one, you can understand because this is not zero. So when you are having a loss, when you are having error is zero, when your model is understanding the model perfectly, then it becomes zero. So still your model is not zero and it's not close to zero either. So what we need to do, we are telling to the model, go back and learn again. Okay, so first iteration is done, second iteration. Your model will increase the values to 0.32, 0.55 or 0.25. Okay, and again this error calculation will happen again back propagate. This is like a student and master behavior. Your student will write an exam and they will delivering you the output. You're comparing with the ground truth, you're comparing with the books, that is your ground truth. And if he scores well and if he's passed, then it's fine. If it is not matching your requirement, if it's not matching your expectations, then you are sending them back again and you are asking them to validate again. Hey, this is how the process will happen. So this is function called this go what is that? Pro and forth the function called okay concept called back propagation. So this is a function called a back propagation. So and what is the cause or loss function? So we used to calculate how wrong our prediction model is. That is how like your loss or cause function is actually helps you to calculate. Your loss function is all about like the actual minus prediction and the whole power the square. And now back propagation. So by seeing this picture, you can understand how the back propagation actually works in the real time. So consider this is your input and this is your output. Okay. So now when you are having input and output, so first back propagation weight is 3, second back propagation weight equals 6, third back propagation weight equals to 9. First iteration you got these values. So it's not matching with the output. So your model is not good. So when you are having a weight equal to 6, your model predictor and it is error is 0 because 6 minus 6 is 0. 12 minus 12 is 0 because it matches. There is no error at all. When it is a double equal to 9, it is matches, not matches. There is an error, negative error, slopes, negative error slopes. So your model is not predicting good. So as a human, by seeing this graph, we can understand that double equal to 6 is the best way to to have a best predictive model. But how did your model knows about? Think about it. So in order to make your model to understand, we are using the function called optimizer functions. So there is a one of a function called a gradient descent. Okay, this gradient descent which helps you to understand out of this iteration which backpropagation will have the best to loss value. Based on that loss values, we will be updating the weights. So consider in this picture, you can see you are having an input, actual output, you are calculating the loss. So actual minus prediction, you are calculating 36%. Actual minus prediction, loss. Actual minus prediction, loss. Okay, you are logging in. So this model, this optimizer will log it in the backend like this 3 comma 36. So this is your weight and this is your loss. Okay, so 3 comma 36. 6 comma 0, 6 comma 0, and 9 comma 36. So 9 comma 36. So it's drawing a graph like this. Now, which weight has the less loss? Here you can see. We got a loss at weight equal to 6. That means W equal to 6 is the best weight. This is how your optimizer will understand the real-time data. Okay, this is how your model will be understanding the data, and there is a lot of things are there. Okay, you can ask me, okay, sir, so optimizer in the sense that will be doing all the jobs. It's not like that. So if you see this picture, one second. Okay, if you see this picture, we are having a various optimizers that are available in the market. So one is like SGVs, and the other one is like GV, and another one is like a mini batch SG. So now here, if you see that everything which will be having the real time values, everything which will be having the real time values in order to compute it. Okay, so now if you see this graph, you can understand your model is initially start learning here. Initially starts learning. That means during the first iteration, your loss is like a 90% or 100%. Okay, a loss starts with 100%. Over the time period, it's over the iteration, backpropagation increases, so it is learning like anything. So its learning is increasing. So learning is happening. That's what the loss is reducing. Okay, because the learning is happening, the loss is reducing. So now this is a state called your model design. Now you can see this particular bottom, right? This particular bottom we can call it as a global minimum. We are naming this as a global minimum, and this error we can call it as a global maximum. Global maximum. This is a global maximum error, and this is a global minimum error. Okay, so this is the overall. So when your model is going somewhere or something else, this is a derivative of cost. So derivative of cost in the sense like your model learned somehow, but it is going in the different direction again. This is a derivative of cost. It should not happen. If it happens, your model is not well in the way we are actually expecting. Okay, so now this is a point of convergence. You can see this is a point of convergence which costs you the minimum cost, which gives you the very minimum cost, and this is the high cost. In real time, it will not be like this kind of a seed curve, and in real time, this is how it looks like. In real time, your learning will be like this, and maybe suddenly it shoot up somewhere else, and it will be learning again, and it will be shoot up somewhere else like this, and again you will be going like this and again. So this is how your model will be. So over the 50 iterations, this is how your learning will be. Okay, initial iteration because this is a one, this is a global maximum, and this is a global minimum. This is a global minimum. Maybe we can consider this is this point of convergence is a minimum cost. This point of point is a minimum cost. We are making that as a global minimum. Okay, and also we will be having a localized values. What is a local minimum? So this is a local minimum, and this is a local maximum. Okay, local minimum, and this is the local maximum. So that means you can ask me, why sir, this your model is will not learn as like this. Will not learn during the time of learning, will not learn completely into the body. Not like recent time. You think about it, because when it is learning, first iteration it learns something, second iteration learns something, third iteration. So over the iteration, your model will confuse because I'm giving you one book, I'm asking you to study. You're studying in well. And I'm asking you to study again and again and again without giving any guidance or without giving any assessments or something else. You will be confused and you will not touch that book. So your model becomes so bad. And again, I'm giving the note of thing like next week you will be having exams. Again, you have started that. Again, I'm postponing the exams. Again, so this is how your model also will do it. Okay, this is how your model also will do it. And if you are doing like this, your model becomes so unstable. Okay, your ball will too unstable based on a learning rate. I'll talk about the learning rate by the way. So, but this is how your model is actually really works in the bank. So global minima and global maximum is a point of convergence and a minimum of cost and the derivative of cost. And here it's a derivative of cost is like this is a derivative of cost. Okay, because it should have like anything because it's almost gone to down and again it should have. So this is a minimum localized cost actually. So this is a localized minimum cost, but sometimes it got should. Okay, sir, when this kind of scenarios will happen, sir, how to avoid this scenario? Sir, I want my model to have a this little slope is fine, sir, but I should not have a big slope. So what we need to do? So that is how we should be focusing on the learning rate. You'll be having the learning rate. If you're having the learning rate like a 0.0001 or 0.0001, okay, your model will learn in a better way. Okay, your model consider this is your learning rate in a sense. You can ask, okay, sir, this is a very less, no, sir. Very less, of course, correct. But if you're having the learning rate is a very less, your model will learn better. But consider the first iteration, your model learned 0.0, second time, third time, fourth time, fifth time, sixth time, seventh time, eighth time, you are learning well. Suddenly your model gets overfit. Suddenly your model gets underfit or something else. It may shoot up. One, second iteration, third iteration, fourth iteration. Think about it, maximum 4 to 5 iteration, we can able to bring them back because that's how my optimism helps. Since I'm giving a 0.001, 4 to 5 iteration, maximum it will go up to this extent. And again it will come back. And again it will start learning. And maybe it will be shooting up 1, 2, 3, maybe 10 iteration, even 10 iteration, it will go up to this extent. Again it will try learning. And again I can stop this process. So I can apply some early stopping. So if my model is over 10 iteration is going again, I'll do early stopping, I'll go stop the process right here. So coming to this point before that, so now your learning rate is really matters to ensure what kind of error you wanted to have. If you are keeping a less learning rate, you will be high. Even if your model gets overfit, it will not extend this much. But if you are keeping the learning rate like 0.1, consider your first iteration it will learn like this, second iteration, third iteration, fourth iteration, fifth iteration. If suddenly it's overfit, 1, 2, 3, 4, it should have like anything. Again, it's coming back. It will bring these somewhat of way. This is the way it has to cross it. These are the long way it has to cross it. Coming back. So this is why we should not keep on bigger now. So that is how this SGD and the GD and the Unified SGD, everybody are they doing the job and your gradient descendant and if you go for like grade SGDs and the SGD will take one data at a time during the time of learning. Okay, it will take one data then for one iteration. For first to back propagation, it will take one data at a time to update the weightage and everything. Gradient descendant, it will take, for example, for one back propagation, if you are having a thousands of data, all the thousands of data it will be taken for the next iteration. Think about it. If you are having a thousands of data at a single shot, thousand data you are taking, and all the thousand data you are going for the back propagation, of course your model will perform much more better. You will be having a good loss, and you will be attaining a very better loss very sooner, and also you will have a better accuracy. But computational power shoot up like anything. In real time, you'll be training with a 10,000 or lakhs of data. For one iteration itself, you are training with like a 10,000, 1 lakh of data, all 1 lakh of data. If you give one iteration, that's it. Your model becomes so heavy, and your computational it's your computational like anything, and it is not it's impossible. That's why GD is not possible. And the SGD, what it will do, since if you take even if you have a 1 lakh data, one data at a time, one data at a time. So this is also bad. This is a so bad, and this is a process wise bad, and this is computational wise bad. So that is what generally we focus for the mini batch SG. So in your skill, you may have like a batch size of 10, right? So batch size of 10 or 8, something else you use. That means 1,000 data set you can take and split them as a batch size. So 10 you can split. So 10 if you split in the sense, you'll be having 100 batch size. So one iteration, first 10 data will go. One iteration, second batch will go. First iteration, third batch will go. So likewise, these batches will happen over the time period, and your model will have a good accuracy. And how this really in real time looks like in the sense this is how. Okay, your model starts here and it learns here, goes here, learns here. In order to get a global minima, it has to take a this amount of long way to come. But if you're using LGD, you can ask, okay, sir, now I'm using GD, sir. I'm using 100, all the 1 lakh of data on the solution. What happens? Your loss starts here, directly goes to you. Reason is because you are computing the entire data on a single shot, but it will not support for the computation. That's what we go for. So SGD in the sense, think about it, it will be taking like a, it will go here, 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 it will go blah, blah, blah. iterations and go walk around, they will come. This is the prime differences between LGD and GD and the millibatch series. So what is Adam optimizer? So nowadays most of the people are reliably directly going for the Adam optimizer. The reason is nothing but because that will be taking care of your job. So it is a adaptive momentum. It is a adaptive momentum. It is a combination of like your momentum and is a combination of your RMS drop. So what it will do, the things you can see like the global minima, global maxima. I told you right. Your Adam optimizer will take care of that. Okay, so it will be focusing with the two things. One is with the momentum. So your model will be focusing on the downstairs. It will be pulling the error will be very, very less. It will be pulling the loss will be so like this. And your RMS prop will decide and what kind of values to update in order to have a good rate. In order to pull this out, it will be understanding, okay, 0.01, 0.2, likewise, it will be focusing on the steps of learning. So this RMS prop function will ensure what is the learning rate to be updated to bring your model to best loss, and your momentum is a guiding force which helps you to reduce the loss. So that is what ADAM is the best function mostly people do use. And apart from this, we have a ADAL graph. Okay, the ADAM and ADAL graph is the most popular ADAM optimizers. I mean, sorry, here again, what is the optimizers technique that you wanted to use it in real time. Okay, and ADAL graph is the gradient based models. Okay, so big learning rate, I told you, right? Jumping over and over. So small learning rate ensures your model is learning at one rate. And this is also Adam optimizer. And if you want me to talk about little equation basis, yes. So loss base, you know what is the loss calculation is generally helps, right? So your loss calculations is for if you're asking me about a GD, your loss calculation is like a summation I equal to 1 to n and actual minus prediction. Actual is all the one lakh of data. Predictions all the one lakh of prediction. So this is for GD, gradient descendant. Okay, this is a loss calculation. This is a loss calculation. For a loss calculation of a GD, and you know, like it's like a y minus y hat. That means actual minus prediction. Actual in the sense one data at a time, one data predictions at a time. So this is for SGD, so stochastic gradient descendant. And generic equation point is like a difference. So it's a work is a so what about a mini by SGD? So mini by SGD is same actually summation I equal to 1 to n, and your loss will be like a y equal to y minus hat, and this is sorry, this is a k. So k sample points. K sample points, this will be there. Okay, so this is how your model generically will be updating the losses based on your these values, and this so typically helps you to and weight values, right? Weight equation is common. So now we are having loss calculation. So weight equal to nu. So how your new weight is calculating? Weight equal to nu, your old weight, okay, your old weight minus learning rate. Your learning rate into the loss calculation. So derivative of loss divided by and derivative of old value. This is an equation. Okay. Okay, you can ask me, okay, sir, where this learning is not what is that loss value filter also? So in order to predict a new weight, so during the backpropagation, in order to predict a new weight, this is the way the old weight we are taking, and we are updating the learning rate. How we are updating the learning rate with respect to the loss value. So this loss calculation, right? This loss calculation, the equation which I drawn before, summation I equal to 1 to n, y minus y. This will vary based on the model you choose. Okay, if you're choosing LGD, so y minus y hat. If you're choosing like k sample, that means the mini minus LGD summation I equal to 1 to 1, y minus y hat over this y. This is how this equation varies, but this still remains same. Your Adam also does the same. Your Adam defines what's the learning rate to be. Okay, so this is how actually your backend technical concepts of your architectures dealt with the optimizer. Optimizer is the brain, is the heart of your functionality that really helps you to fine tune and handle the data in a more peculiar. Okay, so now what is so consider so we'll go for hands-on and for that I'll talk few things. So then I can go for take you to the hands-on. Consider we are going to work with a hands-on called real-time. So we are going to work with a data called like humidity and sorry, temperature and wind speed and invariance kind of value. So we will be having a 3 to 4 components. We will be having 3 to 4 features. Will be having. So this feature we're going to come to the result. If you consider here, I have one example like number of bedrooms, number of bathrooms, square feet. So totally we have a 3 feature. If I give this data set to my model, what if you're giving this data set to linear regression, it takes the data just to predict final estimate. But if you give the same data set to your neural network architectures, if you give the same data to instead of giving machine learning, if you give it to the deep learning architecture, it will be seeing the same data set in a different dimension. Best way for big house, best way for small house, best way for few bathrooms, best way for many bathrooms. Likewise, it sees your problem in a different dimensionality and it will be creating a final price estimation for each and everything. So you can see the different weights for the same question, different weights for the same question. And we will be having the cumulative of all estimates and we'll be having the price estimation. This is the why we have to choose deep learning architecture. If you are expecting a good accuracy, if you are expecting the good estimation over the model, this is how it helps. Okay, so XOR problem statement, I'm not going into this. So in order to resolve your XOR problem statement, we started to work on we have started to work on the neural network architecture. Some kind of linear problems we cannot solve. So like the problem you see here, right? This is a linear problem which you cannot able to solve. Even whatever draw line you draw, you cannot able to separate these 2 dots and these 2 dots. So when you're not able to handle this linear problems, that is the problems we are naming it as the XOR problems. So when your problem statement is the XOR problem statement, then we are jumping into the neural network architectures. And what next? We have a lot of hyperparameters to pull the good accuracy results from the models. One is like a generic one is like a hidden units. How many hidden units you wanted to keep, that you can decide. And what is the learning rate you want to choose, that you can define. And also you can choose like what is the weights and bias. This is quite is not possible from our case, but we can choose binary wise. We can choose it. And hidden units and learning rate, of course, you know. And this is a one of hyperparameter. And if you wanted to other hyperparameters like hidden layers and units and dropouts, they go for initialization, epochs, and batch size, and everything is defined. Your controls, your underfitting, and as well as overfitting issues. Okay, so this is the some parameters and also my So now if you see other hyperparameters, like if your activation function is non-linearity to introduce a non-linear to the models, we can go for sigmoid. And if your problem is like a multi-class classification, you can choose soft ranks. And if you are using the mid layers, like a hidden layers, you can choose like a rectifier activation function. So momentum is all about which helps you to put which direction you want. It's a driving force to pull your model to get a best loss. Okay, and this is all about it. And this is all about it. And we have a overfitting and we have a underfitting issues. What is the overfitting and underfitting issues? Like if your training set error and if your testing set error, both are high. Okay, both are high. Your model is underfitting. Consider your model is learned, your model is not learned the training data, your model is not the testing data. And if it is happening so, then your model is not learning anything. It's not learned anything. That is the called overfitting issue. So training set error. This is not a different predictions. I'm talking about training set error and test set error. Okay, and other one is like a overfitting. When this is overfitting, your training set error is low, but your testing set error is quite high. That means it's marked the entire training data. So that's why it's not able to handle the real time data of this. This is called overfitting issue. This is how actually your model is dealing with the data. And so when your model is working, then how we can able to understand models working. When your testing set error and training set error both are same, both are literally same, like a little higher or short, that is fine. Then your model is working. This is a overfitting and underfitting issue. This one we regularly follow, regularly face when you are working in the development of the course. And some strategies we do have, and some of the strategies to handle fixed underfitting. This is some strategies including the training longer process, adding complex layers, and adding algorithms, which helps you to fix the underfitting issues. And when you wanted to overfit, when you are adding or removing the layers and increasing the dropouts, which liberally helps you to reduce the overfitting issues. And early stopping, so we have our early stopping technique. This early stopping tells you like where you want to stop the model. Consider, as I told before, your model is well learning, and you understood that your model is suddenly shooting up to the bad loss. So you can understand if it is closest to 10 iterations, still it is bad. You can stop the model here, and what is the loss you have achieved and what is the weight you have achieved. With that, you can update the model. This is how your model can help. So that is how we can function. We can call the early stopping. This is the early stopping is pretty helpful when you are working with the real-time deployments. Okay, now I can take you to the hands-on. So before I take you to the hands-on, maybe I can post one video. That video, so to just enumerate yourself back from the learning things. That like Google I/O talk. So Google I/O 10 minutes. It's a project is. So where are we in NLP problem statement and where are we in development of what is that? Just a 5 minutes I post this video. So just to enumerate yourself back from stuffs and I can post this video back and I can 10 minutes of chance to present this video. We have a just to produce it's very question. This is like every year Google I/O talk will happen. What kind of developments they're going to focus on the future and development.
Hello, everyone. Good morning. Welcome to Google I/O. We want to get our best models into your hands and our products ASAP. I'm particularly excited about the rapid model progress. And today, Gemini 2.5 Pro sweeps the LM Arena leaderboard in all categories. It's getting a lot of love across the top coding platforms thanks to all of you.
Gemini 2.5 Pro is our most intelligent model ever. And now that it incorporates LearnLM, our family of models built with educational experts, 2.5 Pro is also the leading model for learning.
I got 2.5 Pro to code me a simple web app. Someone comes to you with a brilliant idea. I'm going to add in a prompt that asks 2.5 Pro to update my code based on the image. And here's what Gemini generates. Whoa. I was able to create this just based on a sketch. But what if it talked? That's where Gemini's native audio comes in.
That's a pangolin, and its scales are made of keratin, just like your fingernails.
Today, we're making 2.5 Pro even better by introducing a new mode we're calling Deep Think. Deep Think uses our latest cutting-edge research in thinking and reasoning, including parallel techniques.
We are in a new phase of the AI platform shift, where decades of research are becoming reality for people all over the world. Introducing Google Beam, a new AI-first video communications platform. Beam uses a new state-of-the-art video model to transform 2D video streams into a realistic 3D experience. Today, we are introducing this real-time speech translation directly in Google Meet.
It's nice to finally talk to you.
Es bueno hablarte finalmente. No puedo esperar a alquilar tu casa.
Our research prototype, Project Mariner. It's an agent that can interact with the web and get stuff done. We released it as an early research prototype in December, and we have made a lot of progress since. And we are starting to bring agentic capabilities to Chrome, Search, and the Gemini app. Let me show you what we are excited about. We call it Agent Mode. Say you want to find an apartment for you and 2 roommates in Austin. You've each got a budget of $1,200 a month. You want a washer dryer or at least a laundromat nearby. Using Agent Mode, the Gemini app goes to work behind the scenes. You might be familiar with our AI-powered smart reply features. Now imagine if those responses could sound like you. That's the idea behind personalized smart replies. With your permission, Gemini models can use relevant context across your Google apps in a way that is private, transparent, and fully under your control. Let's say my friend wrote to me looking for advice. He's taking a road trip to Utah, and he remembers I did this trip before. Gemini can do almost all the work for me, looking up my notes in Drive, scanning past emails for reservations. Gemini matches my typical greetings from past emails, captures my tone, style, and favorite word choices, and then it automatically generates a reply.
Gemini Flash is our most efficient workhorse model. The new Flash is better in nearly every dimension, improving across key benchmarks for reasoning, code, and long context. Flash will be generally available in early June, with Pro soon after.
Gemini Diffusion is a state-of-the-art experimental text diffusion model that leverages this parallel generation to achieve extremely low latency. The version of Gemini Diffusion we're releasing today generates 5 times faster than our fastest model so far.
This is our ultimate vision for the Gemini app, to transform it into a universal AI assistant. In Project Astra, we've upgraded voice output to be more natural with native audio. We've improved memory and added computer control.
Google Search is bringing generative AI to more people than any other product in the world. In our biggest markets like the US and India, AI overviews are driving over 10% growth in the types of queries that show them. What's particularly exciting is that this growth increases over time. We are introducing an all-new AI mode. It's a total reimagining of search. With more advanced reasoning, you can ask AI mode longer and more complex queries.
We're excited to start rolling out AI mode for everyone in the US, starting today. Over time, we'll graduate many of AI mode's cutting-edge features and capabilities directly into the core search experience. That starts today as we bring the same models that power AI mode to power AI overviews. So you can bring your hardest questions right to the search box. AI mode is search transformed with Gemini 2.5 at its core.
It's like having my very own sports analyst right in Search. Search figured out that the best way to present this information is a graph, and it created it. Complex analysis and data visualization is coming this summer for sports and financial questions. Using your camera, Search can see what you see and give you helpful information as you go back and forth in real time. We're bringing Project Mariner's agentic capabilities into AI mode. Search can take work off my plate while still under my control. Search helps me skip a bunch of steps, linking me right to finish checking out. Tickets secured.
With AI mode, we are bringing a new level of intelligence to help you shop with Google. Search dynamically generates a browsable mosaic of images and some shoppable products personalized just for me. To create a try-on experience.
Okay, I'll stop here. It's 6 minutes. Yes. So this is for just to enumerate yourself and also just to understand what's happening in NLP in generative AI. Because in this IO talk, you could have not see that every development is they are focusing on based on LLMs. They are integrating LLMs on top of all source products, and there are tools and everywhere. So in specifically Google Workspace, we could have experience it of. Okay, so coming to the hands-on section here. So here I have my hands-on code. My source code right here. So this is my source code. And this source code, you can see this is my repository. So from this is my repository. My repository first. So within this, my repository. Repository too. The repository from here, and the source code that I discussed is a base skeleton structure is from here, not with the exact data set. By the way, I give you the data set in separate because I have fabricated the data set. I fabricated some data sets. So I have a very few data. So for my development, so for heavy kind of this energy kind of things, since the session is related to that, I have generated the data. So this is how I generated the data by using some Python stores. Okay, so yeah, I have other script also synthesize the script. Only this is just a 10 records. And in the real time, we can able to, if you're having some set of data sets, so for example, if you have 100 or 1,200 samples, you can able to generate a data. Okay, you can able to generate. So here I have just 50 samples, just for 30 to 40 samples. We are having it here. I'm having it here. Okay, you can. That's I gave like a script I wrote. I have generated a different randomized values or not. Also, if you wanted to have a more specific, you can able to add some Boolean conditions, the data sets conditions, not to intersect the values again and again during the generation of the values. Here you could have focused that I have it. This is my data set. So I have a four features which relies here. One is like temperature, another one is like air gradients, third one is like wind speed, fourth one is like humidity. And out of this feature, I do not decide what kind of power output I can derive from solar panel. Okay, this is like a power output of the solar panel. 2.8 kilowatt I can able to derive if I have this feature. So if I have this feature, I can able to derive this output. If I have this feature, I can able to derive this output. So this is how actually we can able to do data derivations using like a solar power data. Okay. Now this is my data set. This is a simple explanation of my data set. All my data set is uniformly distributed values. So from 500 to some 940, so and so it's been distributed for this column, and the wind speed is vibrated ones, like vibrated and since like oscillated ones, and the humidity is like some kind of frequencies is been distributed. And you can see what kind of outputs 2.8 kilowatt and 4.8, 4.5 kind of things we can able to derive. Okay, this is how you are having the values data is being distributed across. And now going to the script. Okay, I hope you all clear with the script, the data set, or what I was explaining. So it's a pretty straightforward data set, nothing much. But I will share this data set. Not sure whether how it helps you. You can just utilize all of it. And here are my repositories. This is my repository I cloned. If I keep some data set, I can clone it locally and I can call them for my purpose development. And here you can see this is my repository. So this is my import function. So this is the import function is like a sequential. This is my framework. So this is my API. So which under API you wanna build your architecture. This is under sequential, and another one is like functional. We are having, and next one is like a dense, another one is like a train distance split, and another one is like a min-max scalar. And the final one is about like a mean absolute error. So totally I have a 5 prime imports right at this place. And the next one is like I'm reading the CSV. I'm reading the CSV. This is my CSV file which I have read about. Okay. And other one is like what are all the feature columns? What are the feature columns? These are the feature columns. Temperature, the gradients, wind speed, humidity. These are all my feature columns. And what is my output column? It is like a power output kilowatt. This is my output column, X and the Y. Okay. So this is my input and output derivations. Next one is a scale. I need to do the scaling because if you see my data set, you will be having these are the values. And what you can see in this temperature 2020 to 24 something else, the variance, this is so far, wind speed so far, what your model will think. Okay, if you're not even aware of this data set, if I don't give this labels, or if I don't have this what is that the feature names, you will understand like okay, this is a very important feature. So this is an important feature, this is a rest feature. This is how your model also will understand. If the numbers are big, your architecture will think that is a very important feature. If the numbers are small, your architecture will think that is a prime least important of the data set. So in order to make them so biased, in order to make them so equalized, you need to convert them into some 0 to 1 range. So this value will be converted into 0.002. And this point will be converted into 0.0, so 500, and this value will be converted to 0.00 something else. Likewise, it will be converting these values. Okay, this will be converting these values into different ones. So 0.52, this one is 0.05, something else we are converting, and these values will be converted into 0.00027. Likewise, it will be converting all the values between the range of 0 to 1. That's how this particular range tells you I'm creating the object for X scalar to handle the X data sets, X columns, for Y columns for this object. Okay, here I'm transforming the data set of the X columns. I have transformed. Transforming the Y columns, I will transform. Okay, here I have a training and a testing set. Here I have a training and a testing set. So 25% testing set, 75% training set. Likewise, I can able to plan the data set. This is how actually which helps you to develop it. Okay, so now your training and testing set, of course, you know, so I don't want to much talk on this. So now I'm having a neural network model. So here you can able to see I have a sequential API. Okay, so this is a API in the sense that this is a place where you construct your architecture. This is a sequential API. Okay, you will be having like a dense layer and input dimension 4. What is input dimension 4? 4 input features are there. So one is like a what is that? Temperature, irradiance, wind speed, and the final one is something else. Okay, something else. Okay, and you have a 50 neurons. You will have a 15 input neurons. Okay, so you have 15 input neurons, I mean hidden neurons. And next one is dense 100 hidden neurons. Okay, 100 neurons. And the third one is again 50, so and so and so 50. And the final one is like a 1. So this will tell you what is the power kilowatt you will be deriving from here. And you can see ReLU, ReLU, ReLU. So here I initialize the ReLU evacuation function. Here I initialize the ReLU evacuation function. Here I do ReLU evacuation function. And the final output function is a linear because that is a linear data set. Okay, that is a linear data set. Okay, because your output is totally rely on what kind of value we going to generate over the development. Okay, next one is you're compiling the model. So what kind of error rate you wanted to focus on? MSC. So mean square error. So summation I equal to 1 to n y minus y hat whole power square actual minus prediction. So mean squared error, you are calculating the mean of it and you are taking the square of it because you are applying the penalizations for the minimalized error. Okay, so that is what mean squared error you are using. So you are applying the more penalizations for the squared errors. Okay, that's what this is one thing. And optimizer here we are choosing is like a GED. This decides you out of 50 iteration by propagation, which propagated value has a high intensive results overall. This is how your compilation actually defines and helps you do this one. And the next one, you are training the models and you are training the model with the training data and labels and epochs, 50 back propagations. Back size you are defining here is the 8 of back propagation you are designing, and this is a verbose 2. And so verbose 2, that means the 2 lines of code you wanted to also 2 lines of print statements you want to consider with and shuffle into. That's all of this. Now you are doing a job lib. What is this job lib? Actually tells you I'm storing my train object, test object. So my so training what is that preprocessed data and white label preprocessed data. I'm just storing them. So you already have preprocessed, right? That means you have preprocessed X column and preprocessed Y column. Just storing that object. That functionality I'm storing it as an object because this object has a capable of how to pre-process your data. So to pre-process your data, here we are focusing on pre-processing the standard scales. That's what we are doing right here, and you are saving the model again. So you are saving your model right again here. So next to one, what we are doing again, one is like the evaluation. So we are focusing on the evaluations. So this evaluation is simple evaluation I'm focusing on. So I'm not doing much complicated. Model.predict. I'm predicting the model. Okay, predicting what kind of data you're gonna predict. Train data. You can ask me, okay, so why we are taking training data? We should have picked like a testing data. Why we choose training data here? And you could have asked. So I told you, right, in order to ensure your model is trained with the overfitting or fitted with the underfitting. So in order to do this, I require limit error rate. I require error rate. So that's what we are generating a training set error and as well as a testing set error. So I'm taking a training set error. Okay, here you are having the training set error, and here you are having the testing set error. Okay, so your training data and the training data. Okay, prediction and as well as here you can see like we are inversing the form of the data. So why we need to convert them to the actual data. Okay, we have to convert them. Yeah, coming to the point. So we are inversing them because I have to calculate the MAE error. So sorry, I have to calculate the MAE error by using this kind of what is the mean absolute error, because mean absolute error I'm focusing it here. So that means I'm not applying more penalization. If my error, if there is some errors, I'm not applying much penalization. So that's what I'm using a more mean absolute error here, because our problem statement is not that intensive. If your problem statement is like what is that finance or statistics or medical, then you have to apply the penalization for your error. So you will have to square the error, applying the more penalizations of that. But when you come forward here, it's a very pretty straightforward. It's not much important to be focused on in that direction. That's what it is we need to be. And all right, so coming to the point again, and here I'm calculating the training set error, and here I'm doing the same process for calculating the testing data. So once you are done, you can see that here your training model is training and your loss is there, and loss is literally reducing over the time periods. Saying that your model is learning. Your model is learning here. So that's how your model is learning. Now you can see like a training setter and a testing setter 0.1 kV and 0.6 kV. So what this training setter and the testing setter is nothing but your model is learning in a maximum. So if your model is predicting like a for your query, it's a 2.8 kV in the sense, for 2.8 kilowatt in the sense, plus or minus 0.113 or plus or minus 0.06. So training set error and the testing set error bit are fine, not that much. That is how your model says. Okay. Now next to one you can see like this is the one you can able to see, and here you can be able to see one thing is like a testing data set. Your testing data sets, you can see like I'm giving this testing data, I'm giving it to my model is predicting that. Okay, so you're giving so and so data, and your model is predicting the solar output is like a 5.6 kilowatt. That means a plus or minus 0.14, 114, or plus or minus 0.061. Okay, this is how your model is. Okay, so it's all about the explanation. Any doubts, any queries from the participants end? I'll give my contacts, by the way, with all of you. You can reach me out if you have any requirements or queries. You can reach me out. I can help you out. Any queries or any doubts, I can help you out. Because I have other meetings to jump forward.
Participants, if you have any queries,
Any doubts?
you can post doubts. Participants, if you have any queries, just post in chat box. Otherwise, unmute your mic and ask it. If there are no queries, I'll go into questions, sir.
Sure, sir. We can click on the same, sir.
Okay, sir. Thank you, sir. Thank you so much for your valuable presentation regarding the renewable energy data using the neural network. Thank you so much, sir.
Thanks a lot, sir. It's my pleasure to be here. Thanks a lot.
Thank you, sir.
Okay, good evening, everyone. Thank you so much.
Participants, there will be the feedback posted in chat box. Kindly fill the feedback form